Okay, we're going to move into coming up where we have energy in the atmosphere. Think of it like a car. You need gasoline to provide energy to your car to make it go. Well, something has to do that for the atmosphere. And what that something is the sun. So this week we're going to start talking about the sun a little bit and understanding the sun and how it works and just what we can get from it. So how does the energy flow into and out of the atmosphere? If you don't have a balance on that, think about it. If you kept getting more and more sunshine and the sunshine was hotter and hotter, the Earth's temperature is eventually going to get way too hot for us to live. But thank goodness our sun's pretty stable. It doesn't vary a whole lot in the amount of energy it fluctuates out relative to what reaches the Earth. So we have a fairly stable climate system as far as the sun bringing energy in. So let's look at the energy. Energy is electromagnetic radiation. You hear electromagnetic radiation all the time in radio waves. If you're listening to the radio, if you look outside, you see light. That's electromagnetic radiation. So we're going to talk a little bit about wavelength here. Wavelengths are just the distance between two crests of a wave. It's a wave. I mean, it really is just that as far as electromagnetic radiation goes. So I usually kind of convert it in my mind to being at the ocean and getting hit by waves. When one wave hits you, you have the peak. And by the next wave hits you, that's the second peak. That's the distance between the two waves, however long that distance was. And you can deal with time as well as that. So any number of waves passing you at one location, the faster they pass you, the shorter the wavelength. And there are times when I go in the ocean swimming and the waves are one right after the other. You just feel like you're in a washing machine. And that's a fast wavelength. All objects absorb radiation, electromagnetic radiation. The amount they absorb it may vary a little bit, but most objects can be considered a black body. That is, they absorb all the radiation it receives and emits it, and all that energy back out of it. A true black body would be a perfect absorber and a perfect emitter. So this is how we develop some mathematical laws for the radiation. For example, Wend's displacement law. If you know the temperature of the object that's emitting electromagnetic radiation, and we'll say it's the sun, then you can estimate the maximum radiation wavelength that most of it is. Since the sun is extremely hot, you know that wave is going to be very short and actually falls right into the visible range. Here's another one, the Stefan-Boltzmann law. This is just the total amount of energy emitted by an object. Think about it. If the sun, way, way hotter than the Earth, and you put it to the fourth power, that means a ridiculously amount more energy is coming out of the sun than actually coming out of the Earth. So that's what is going on. The amount of energy emitted, way more being emitted from the sun than being emitted from the Earth. One of the interesting things is Earth is approximately 96 million miles from the sun. So if you were to double that distance from the sun, how much radiation would then arrive at that new planet, wherever it was? Well, there's an equation for that. The amount of energy would be 1 over whatever the radius squared is. So if you double the radius from this Earth, you would make it 1/4 the amount of sunshine, 1/4 the energy you would be receiving at that planet. You go the other way, you get closer, you would make it obviously more. So if you make it 3 times the distance from the Earth, It would be 1/9. So it all depends on how far it is from the Earth. So that's why our planets that are further from the Earth, further from the sun, receive less and less solar radiation. And you can see it goes down pretty quickly if you're squaring it. Now we're going to talk about how the sun's radiation hits the Earth. This is kind of a little bit more challenging. Think about it if you have a flashlight. If you hold the flashlight directly over an area, you have a pretty intense beam of light, just hitting a little small circle. Now, if I bring that flashlight to the side, lower it down, that area of energy, the lighted area now is not quite as bright, and it's covering a larger area. So there's two things that happen there. One, the area that the same amount of energy is coming out of the flashlight, but now it's covering a larger area, and it's going to appear weaker generally over that area. So what does that mean as far as the Earth? Well, if you're right on an equinox, when the sun is right over the equator, think about it as being a flashlight. It's going to bear down very intensely right at the equator. Oh yeah, but that same flashlight now, look at it when it gets to the North Pole, it's going to be at a pretty steep angle. So there's not going to be nearly the amount of radiation reaching North Pole or the South Pole at that time. So that is why the amount of solar radiation is much greater in the equator or around the equator than it is further north or further south, because it's not hitting directly on the Earth. Now, when the Earth starts tilting towards the sun, like we up here in the northern hemisphere are right now, and a matter of fact, here in a couple of days, it's going to be the summer solstice, or the most sunshine we're going to ever receive, the most intense sunshine, will be actually occurring right then. So with that, it impacts the amount of solar radiation that arrives at any location. So, for example, in the northern hemisphere here, say you go to Rockport, Maine, New York, you can see it really goes down in December when it's the lowest amount of energy, because that's when the sun is furthest from and more of an angle up here in the northern hemisphere, right on December 21st. Then it starts picking back up again. So I have a good friend that lives up in New Hampshire, or Vermont actually, Burlington, Vermont. And he hates summer. So he will let me know when June 21st arrives, because he points out to me immediately the sun is now moving back south, winter is coming. But I can always point out to him on December 21st that the sun is returning, and I know summer is coming. So you can see, even though temperature lags across the Earth, the solar radiation varies from season to season, and actually is least intense on December 21st in the northern hemisphere, and the most intense on June 21st. And here it is. As you can see, as the Earth rotates around, it never changes its tilt. But because of its relationship to where it is in terms of the sun, it looks like it has. So how much then of all this energy comes in and makes it to the Earth's surface? Well, there are things called scattering, reflection, and absorption that delete some of that energy. Literally, don't let it get all the way here. So what is scattering? Well, scattering is basically when a particle, an energy hits some kind of particle. It could be a dust particle, it could be clouds, and it's going to scatter that radiation in all different directions. Some of it's going to head back the way it came in, some of it may head in a different angle. You can see here all different directions. And so that is actually what causes our sky to be blue in the daytime. That kind of scattering occurs in the atmosphere. So not all the energy from the sun is making it through the atmosphere to the earth, or even into the atmosphere. Then there's a thing called reflection, or albedo. You walk outside in the wintertime, you have bright, fresh snowpack. You got to put on sunglasses, to be able to see because it's so bright. Why is it so bright? Because of the albedo of the snow. Snow is highly reflected. It's like a mirror for radiation, for solar radiation. It reflects a lot of that solar radiation back out into space. So that impacts the amount of solar radiation available, amount of energy available at that location where the snow has fallen. Absorption. Absorption, really, you can notice it in the stratosphere where you have the chemical reactions taking place and absorb a lot of ultraviolet radiation. This keeps the upper stratosphere a whole lot warmer than it would otherwise be. And it significantly reduces the intensity of that ultraviolet radiation. And that is all based on the ozone layer. So the lighter the surface on the Earth, the higher the albedo. So think about it. If you're in a forest is very dark. It's going to absorb a lot of solar energy, a thick rainforest. The oceans are very dark compared to land. Deserts, more reflection, less solar radiation, maybe. So here is the actual totals. Reflected by the whole Earth's atmosphere system, 30%. Absorbed by the atmosphere, 23%. And 47% then is absorbed on the Earth's surface, making up a total of 100% of that radiation that reached Earth. So we've accounted for it all. And there's another factor that keeps Earth warmer, however, and that's the greenhouse effect. So if you talk about solar radiation comes in mainly in ultraviolet. The Earth, not nearly as hot as the sun. Matter of fact, it's way cooler than the sun. But it's still a black body. It's still emitting infrared radiation. Just at a low, the wavelength is much longer. That's why it's called infrared, because it's leaning toward the red spectrum. So the Earth emits this long wave radiation. And then there are these greenhouse gases that absorb long wave radiation. They don't absorb ultraviolet. They absorb long wave radiation. And what are they? The principal one is water vapor. Next one is carbon dioxide, ozone, and methane. And all this radiation can pass into space with little or no absorption in the atmosphere. And you can see there are different windows here. If you ever look and go to a satellite weather page that the Weather Service puts out, you'll see 16 different weather channels. Each one of those represents a wavelength. There are wavelengths that can show where different radiation or gases are emitting in infrared radiation. By looking at that, we can tell things about water vapor. We can actually tell things about carbon dioxide. So one of the things to note here is where there's more humidity, you're going to absorb more of infrared radiation. So the nighttime temperatures are going to be warmer. That's why in the deserts, where there's not a lot of humidity, the night times are very cold, even though the daytimes will be quite hot. While in the tropics, the night times will be kind of mild. That's why in the summertime, where you are, when the temperatures are rising in the summer, and you get these really humid air masses coming in, what happens is the nighttime temperatures warm up. They don't get as hot. They don't get as cool, excuse me. And then the calendar effect is measuring CO2. That's all it measures. The Keeling curve is based out in Mauna Loa, and it's shown, matter of fact, it's reached a new high this year again of carbon dioxide. But all it measures is that. There are many other greenhouse gases that we've just talked about that impact the Earth's temperature. So with that, I just wanted to do a real quick look at climate And here is, for example, Nome, Alaska. Notice how the temperature, average temperature, doesn't change a whole lot in January, and then gradually begins to go back up significantly in March, April. Guess what? The sun just rose. The sun didn't come up there until then. So it doesn't change a whole much in the wintertime. But boy, it does it change quickly upwards until the middle of June, early July, and then it begins to settle, keep about the same, and then it will drop back off again as the sun moves south. Another place you can look at normal temperatures here, for example, is Mansfield, Ohio, which just shows you the normal temperature for the month or daily normals. If you were to look at daily normals, normal high temperatures in January, they don't reach their coldest until the end of the month. And then they begin, and they are the coldest from the end of January to early February. So there's a time lag here. We're going to understand more about that in the next chapter. And the same holds with the lowest temperatures. The lowest temperatures are the end of January into the very early part of February. So hope you got something out of this. Let me know if you have any questions.